Hi everyone. So as always, we start with the learning objectives. These is the things that we're going to be learning today. This you should already know, but we're going to go through it again. And all of this stuff you've never seen before, especially things like equation of state, what an ideal gas is, and so on. So let's get started. Okay, so imagine that I have a tomato. So this is my tomato. I don't know, but it actually looks like a heart, but it's a tomato. Now it's a tomato. But it looks like an apple, but still it's a tomato. Anyway, I have a tomato and I want to cut it. So for this, I use my finger. So this is my hand, and I use this finger over here. And when I put my finger in here and I try to cut the tomato, I can't. Now, if instead of my finger, I use a knife, because I'm extremely clever, turns out that I can cut the tomato. But the force I was doing is exactly the same. So the force finger is exactly the same as the force that I was doing with a knife. So how come I managed to cut the tomato with a knife, but not with my finger? Well, the reason for this is pressure. When I'm using a knife, I'm doing a lot more pressure than when I'm using a finger. So let's think about what pressure means in this context. Well, the only thing that changed here is surface area, right? My finger has very little surface area, very large surface area, and my knife has very little surface area, which means that the force is distributed over a much smaller space. So there's more force per unit area, and that allows me to get through the tomato. So if I had to find a formula for pressure, I'd say, well, here's my pressure. Now, of course, the more force I do, the more pressure that I have. And the less area that I have, the more pressure that I do. Therefore, pressure has to be inversely proportional to the area. Let's think about the units for a moment. Well, the units of pressure, remember this means units, have to be the units of force over the units of area. So in the international system, that's newtons per square meter. But because we don't like writing so much, we call that pascals. So newtons per square meter are called pascals. So that's pressure. However, there's a little difference here, because here, well, imagine that I have a table here, so let me just draw a table. Here's my table, and I'm doing some pressure on it. So with my hand, so again, this is my hand. Okay, I'm terribly deformed. That's supposed to be a hand. I'm doing the force, but I'm not doing it straight down, like this, but I'm doing it to the side, like this. Now, stop the video and think for a moment. Will there be more or less pressure if the force is exactly the same, but the angle is not the same? In which case will I have more pressure? Will there be any difference? Now, hopefully you pause the video and you did your own thinking, but obviously this does more pressure than this, because in this, part of the force is lost. This part, the part that goes this way, is lost. And the other force, the only part of the force that we care about is this one, which is the projection of this force in here. So if I call this angle theta, which is the angle to the normal, see, this is the surface, this is the normal. Yep. So if I call this angle theta, the pressure that I'm doing really is not F over A, but it's F times the cosine of theta. Remember, the projection horizontally, it's the cosine, it's like the shadow. F cosine theta over A. And I think you didn't do this in the IGCSE. So this is a little modification that we need to include in our pressure to take into account that the direction in which I do the force matters. But believe it or not, this is about gases. So we're not going to talking about pressure that solids do, but we're going to talk about the pressure that gases exert. And you might remember that gases are made of molecules, and these molecules are placed randomly and moving in random directions. And what happens is that these molecules collide against the walls, and it is this collision that creates the pressure on the recipient. Now, on the container. Recipient, is that a Spanish word? Well, I'm not sure. Anyway, so we have a gas in a certain volume V. V. And it's creating a certain pressure P. And we would like to know what is this pressure related to? And the first thing that one may think is, well, maybe it's related to the type of molecules that we have here. But since we're considering an idealization, we will be assuming that these molecules are perfectly round and all the same. They don't interact with each other. So we don't really care about the type of molecules that's in here. In fact, we know from before that the pressure will increase with temperature because these guys will bounce onto the walls harder. And the temperature is related to the average kinetic energy of the molecules. And hopefully you remember this from thermal physics. So now that we know this, we can ask ourselves, well, so if we don't care about which type of molecules we have here, what do we care about? And actually what we care about is, well, first, of course, how fast they're going, so the temperature, but we also care about how many of them there are. Right? So if there's a lot of molecules, there will be more collisions, and therefore there will be more pressure. If there's very few, we'll have less collisions, and therefore less pressure. Now, measuring things in molecules would be a pain, because remember, there's a lot of molecules in 1 liter of gas. However, we have a quantity that we know that gives us an idea of how many molecules there are in a place, and still gives us numbers that are easy to deal with, and that's, of course, the mole. So we're going to be measuring things in moles just because it gives us an idea of how many molecules are there are in a gas, and it's not a huge number, like 6.23 times 10 to the 23, which is way too big. Now, there's a lot of gas laws, and they're all related to what happens to a gas when you keep one of these three things constant. So we have pressure, volume, and temperature. And then if I keep pressure constant, then volume and temperature behave in a certain way. If I keep volume constant, then it's pressure and temperature that behave in a certain way. And if I keep temperature constant, then pressure and volume behave in a certain way. The first thing we're going to do is look at what happens when temperature is constant. So now we're not concerned about temperature. We have a certain gas at a fixed temperature, and we want to know what happens when we change either of those things. All right, so this is called the Boyle-Marriott Law, and because it was discovered by Boyle and Marriott. And it's actually pretty simple. What they found out is that if I have a certain gas in a volume, and then I decrease this volume, so I have this box, and now I have this box here. Now, what will happen to the pressure is that it will, of course, increase, and that makes a lot of sense, right? So here I have a bunch of molecules that are bouncing around. If I decrease the volume, then the molecules are more packed together, but I still have the same, so I have more collisions per unit area. Therefore, as the volume goes down, the pressure goes up. The other way around, if I make the volume bigger, so from here to here, then the pressure will go down. What happens then is that the pressure times the volume are always the same. So P times V is a constant. And that's Boyle-Marriott's law. Now careful, again, this only works for constant temperature. If temperature is not constant, then this does not apply anymore. We need to look at what happens. So if, for example, if the temperature went down, it's very likely that TV will go down. If the temperature went up, then PV will go up. But at constant temperature, PV stays constant. Now we're going to take a look at what happens when pressure is constant and V and T are not. And I've developed this extremely clever color code where the thing that's constant is blue and the thing that's not is white. And that's why I studied physics, to come up with these amazing ideas. Now, so imagine that I have, again, a gas in a certain volume. Could be a box, could be a balloon, could be a bottle. And this volume can expand. So I'm not fixing the volume. I'm allowing this thing to expand. So one way to imagine this is I have this cylinder. And in this cylinder, there's a little piston here that has no friction and can move up and down. Okay, so I'm allowing this thing to freely move up and down. And inside here I have a gas. Okay? I think this is the easiest way to imagine it, because otherwise it's hard to imagine a volume that can freely expand, right? Unless it's a balloon. So okay, I have this gas, and I decide to increase the temperature. So temperature goes up. Now, as temperature goes up, these guys here start moving faster and exert more pressure in here. But because it is movable, this doesn't have to stay here. This can go up. So the extra pressure makes this go up until the force of the gas and the force of gravity on the piston are balanced, which means that the pressure here has to be exactly equal to the pressure that there was before. Therefore, pressure has indeed stayed constant. And now what happened to the volume? Well, obviously the volume went up as the temperature went up, right? So we have that when temperature goes up, then, the volume also has to go up. And that makes perfect sense, and, you know, it's something that you can see in your everyday life. I don't think anyone has any problems understanding this. Now, so how can we express this mathematically? Well, since they both increase, we can't say that V times T is a constant, but we can do the opposite, right? We can say, well, V over T is a constant, right? However, this doesn't quite work. At least it doesn't work if we use the naive units for temperature, and you'll see what I mean in a moment. So let's zoom out this thing. Excuse me. So imagine that I have a certain gas, and I start increasing and decreasing its temperature, and I plot. So I make a graph like this. So here's my temperature. My temperature is in the x-axis, and the volume is on my y-axis. Okay. Now, if I start measuring temperature and volumes at constant pressure, I will get something like this. So something that goes like this. And indeed, this seems to follow a straight line. You do know, though, that in practice these things are going to be a little wiggly. However, this thing doesn't go through zero. This thing's going to do something like this. And actually, if I start measuring things, so this is in, of course, degrees centigrades. So when I'm at 0, then I keep cooling the gas down, and I will see something like this. Sorry, wrong color. So, now I can make a regression line, and it will look something like this. Best fit line, sorry. You call it best fit line. Actually, it's called a linear regression, but I digress. So as you can see, we've got a line that does not go through 0, but eventually reaches this point here for 0 volume. Now, of course, it's impossible to have volume that's less than 0. That would be very strange indeed. So this is telling us something about temperature, right? It's telling us that I can't go any colder than this, because if I did, I would have a volume that's less than 0, and that makes absolutely no sense. So I do this for one gas, and I do it for other gases, and I always get the same. I will always get a line, and it always ends up at some point here in the x-axis, where the volume will be 0. And what's really, really impressive is that this point here is always the same temperature, which is minus 273 degrees centigrades. And that tells us something. That tells us that it is impossible to achieve a temperature that's less than this. And these led physicists to think, well, maybe we're measuring temperature in the wrong units. Maybe we shouldn't be measuring temperature in Celsius at all. We should be measuring temperature in a way that makes it impossible to go below this temperature, that makes this temperature somehow special. And that's what the Kelvin scale does. I think you've heard about the Kelvin scale before. In the Kelvin scale, all we do is we call minus 273 degrees Celsius, and we call it 0 Kelvin. And we call this thing the absolute zero. And we say, well, it's impossible to get a temperature smaller than the absolute zero. Actually, it's impossible to get to the absolute zero, because that would also mean zero volume. And it would also mean that molecules are infinitely still, which is impossible. So if we do this, then we get a graph like this. So we actually get exactly the same thing, but displaced to the right. So we will get a line like this. And in this case, yes, we can see that the slope of the graph, m, will be equal to v over t, and it will be a constant for all b and t, as long as we keep pressure constant. And in this case, there's no b-intercept. So there's no, y-intercept, and therefore there's no b in the graph. So this holds up. This is the volume temperature law. It has a very original name, and it's just telling us that v over t is constant if we use the Kelvin scale. If we use the Celsius scale, it will be v over t plus 273. Well, actually, plus a constant that we would have to determine is constant. Okay, so how about P and T? Well, in this case, we're going to get the very originally named pressure-temperature law. And again, we keep the volume constant, and we increase the temperature, and then, of course, these little guys start moving faster and faster and faster. They hit the walls harder, therefore the pressure also increases. So we have temperature up, pressure up, which again would tell us that P over T is a constant. But again, that doesn't work because we need to do things in Kelvin. If we do things in Kelvin, again, we will get P over T is a constant and T in Kelvin. Nothing more to say here. That's pretty much it. Okay, so now we know enough to introduce something called the equation of state. And the equation of state is a combination of all these equations that we've been seeing before, but it's better in the sense that if we know the equation of state of a gas, we know pretty much everything there is to know about it. We can make predictions about its state. As long as we know PV, we can find T. If we know T, we can find PV, and so on. The only thing is that this is restricted, in at least the one that I'm going to show you, to ideal gases. Now, an ideal gas, we've talked about this before, but I'm just going to go over it again, is a gas where I'm assuming, one, that the molecules are perfectly spherical, and two, that they never interact. They only interact when they hit each other. So when they're infinitely close. So when they hit each other, they just act like billiard balls, and they bounce. But there's no other interaction. There's no potential energy. They only have kinetic energy. That's what an ideal gas is. Most gases behave like ideal gases as long as the temperature is high enough and the density is low enough. If the density gets too high, then weird things start to happen, and we need other equations to describe the gas, because then potential energy cannot be neglected anymore. Okay, so let's try to think about what we knew. So we knew PV equals constant, we knew V over T equals constant, and we know that P over T equals constant. And all those things were only when the other variable was kept constant. Now, let's think about this one for a moment. So I have PV equals constant, but of course, if I make the temperature higher, either this is going to increase or this is going to increase, which means that the product is going to increase, right? So what I really have is PV is proportional, and this little symbol means proportional, is proportional to the temperature. And now our task is to figure out the constant of proportionality. And actually, we need there's two in here, so we need to figure out two numbers in here. Okay, so let's do that. Let me zoom out. So first one, well, let's think about the number of molecules in here now. The more molecules that I have in here at the same temperature, the more pressure and volume that I'm going to have, right? Because there's going to be more molecules well, instead of a molecule, I drew a bin. Anyway, these molecules are going to be bouncing against the walls. More molecules, more bounces, more pressure. So PV should be proportional not only to T, but to the number of molecules. Now, because we don't like dealing with numbers of molecules, what do we deal with? Yes, I just heard you say moles. Very good. And the number of moles, we call it N. Okay? So we have that PV is proportional to NT, where N is the number of moles. Good. We're doing great. And now we need some other constant. And in this case, it's just a constant. So we know the more moles, the more PV, the more T, the more PV. And then there will be a constant of proportionality simply because nature does not measure things in R units. Now this constant is called, again, very originally, the gas constant. And it's called R. So PV is nRT, where R is the gas constant, and it has this value. R is 8.31 joules Kelvin minus 1 mole to the minus 1. And that's pretty much it. This is the equation of state of an ideal gas. If you know this equation, you can make any prediction you want about an ideal gas as long as you have 2 pieces of information out of the 3. Alright, so now it's time to look at the learning objectives to see whether I actually taught you what I was supposed to. So state the definition of pressure. You should be able to, it's just a formula. State the equation of state for an ideal gas. We just did. Describe the differences between an ideal gas and a real gas. Yes, we did that. Remember, an ideal gas, there's no potential energy. Molecules are perfectly spherical. They don't interact. Now, finally, we did this. We talked about the absolute zero, and we know how to find it. And this, well, that's up to you. We're going to be doing this during the week. See you later.